Sara Murciano from Caltech that just moved there from SISSA. Sara, do you hear us?
Yes.
Perfect.
Can I share the screen?
You should be able to do so.
Yes.
Okay, so the subject of the talk is a probe of symmetry breaking from entanglement. Sara, the stage is yours.
Okay, thanks. So, hi everybody. Thanks for the opportunity of giving this talk. And let me also say happy birthday to Professor Caracciolo. Okay. You can see my screen without all this.
Yes.
Okay. So as Pasquale said, in this talk I will try to describe what we are currently working in with Filiberto, postdoc in SISSA, and Pasquale, of course, in studying this interplay between entanglement and symmetry, and in particular we'll focus on how entanglement can be useful to quantify how much a symmetry is broken in a system. Before going into the details, I will just summarize what are the main definitions in this game between entanglement and symmetries. So usually, if we are interested in the bipartite entanglement between two complementary parts, A and B, the setup that we consider is the following. We start from a pure state, psi, that lives in this full Hilbert space, H, that admits this factorization into HA, containing the degrees of freedom in A, and HB, containing the degrees of freedom in its complementary part. Then we can build a density matrix, ρ, as this projector, and by tracing over B, we obtain the reduced density matrix, ρ. Now, one of the most popular measures of entanglement between A and B is provided by the Feynman entropy, whose definition is reported here. So it's minus trace ρ log ρ. And the problem of this definition is that it involves a reduced density matrix, so an operator and the log of this operator. So let's say an easier way to compute this quantity is to look at another family of entanglement entropies, which are the Renyi entropies. They are defined in terms of the trace of ρ to the n power, that now is a scalar quantity. In particular, it can be seen as a partition function on the N-Sheet-Riemann surface. Here I have the picture for n equal to 3. Basically, one can consider n identical copies of the system and join them cyclically along the cut that corresponds to the subsystem A by identifying the first with the last one. And if one does an analytic continuation in n to the Renyi entropies for to any complex values of n and takes the limit n going to 1, one recovers the Feynman entropy. What happens in the presence of a symmetry? Well, let's consider the generator for A1 symmetry, so for the abelian case. In this case, if the charge is local, meaning that it can be split into the charge in the subsystem A and the charge in its complementary part, and if ρ commutes with Q, so basically the pure state that I introduced before is an eigenstate of the total charge operator. Once we trace over B, we obtain that a similar commutation relation holds at the level of the subsystem A. So we have this commutation relation between ρ and Q of A. This implies that ρ admits a block diagonal decomposition into the eigenbasis of the charge Q of A. And each block is labeled by this small q that basically are the eigenvalues of the charge in the subsystem A. And if we extract from each of these blocks P of Q, so the probability of finding Q as an outcome of the measurement of the charge in A, we obtain ρ of Q, which is a reduced density matrix in each charge sector, properly normalized now because we have extracted a trace. And therefore, we can plug this reduced density matrix in the definition of the von Neumann entropy, and we obtain the symmetry resolved entanglement entropy, which is basically a measure of the entanglement in a given charge sector. Now, if we should compute the symmetry resolution of the entanglement starting from its definition, it will be highly non-trivial, because we should know the entanglement spectrum and its resolution in the different charge sector. However, we can apply the following trick introduced for the first time by Goldstein and Sela some years ago. So we consider the Q moments of the reduced density matrix, this calligraphic Z. And we plug the Fourier representation for the projection operator for this P of Q. By doing so, we connect the Q moments of the reduced density matrix, in terms of which we can define the symmetry resolved Rényi entropies, to the charge moments, these Zn alpha, that are the charge moments of the reduced density matrix. And these charge moments can be seen as a partition function on an n-sheet Riemann surface again, but now with insertion of a flux, in such a way that when the field goes around the entire surface, it will pick up a phase alpha. So in principle, one can use all the tools that are known to compute the partition function on the n-sheet Riemann surface, but now take into account that in going from one sheet to the other, the field will pick up an additional phase depending on alpha. So this is these are the main definitions that concern the use of entanglement in order to analyze an abelian symmetry in this case. And the questions that we recently tried to address with Filiberto and Pasquale was, okay, but what happens if our reduced density matrix is not block diagonal, or in other words, if the symmetry is broken? So there will be some out of diagonal elements that basically break the symmetry. And okay, our idea was to consider another reduced density matrix, this rho A of Q, which is basically obtained by projecting rho A in these blocks. And we have defined the entanglement asymmetry, so this new quantity, which is basically the difference between the entanglement entropy associated to these two reduced density matrices. And this is our new quantifier of how much the symmetry is broken in a system. It satisfies these two nice properties, so it's a positive quantity, and indeed this can be seen also the relative entropy between the two reduced density matrices, and it vanishes if and only if the symmetry is restored. And so basically rho A is equal to rho A of Q. How to compute this object? We can still define a replica trick for it, so for any integer values of n. And once again, by plugging the Fourier representation of the projection operator, we can connect the trace of rho A Q to the n power to the charge moments, where now these charge moments have, let's say, a different structure with respect to the ones that I showed you before, because rho A and Q of A do not commute. And so we have to preserve the order when we do this kind of computation. Let me just comment that if these charge moments do not depend on this vector alpha, basically it means that the trace of rho A of Q is equal to the trace of rho A to the n power, and basically delta S is equal to 0. Now, in order to show that the tool that we have introduced is an efficient way to probe the symmetry breaking, I will do an example. So if we consider a ferromagnetic state like this, so we have all the spins aligned, the density matrix that we can build from this state does commute with the total transverse magnetization. So delta S is equal to 0. While if we tilt the spins of the same angle theta, the density matrix built from this tilted ferromagnetic state now breaks the U1 symmetry, so it does not preserve the total charge Q. And so delta S is different from 0. Now we choose this tilted ferromagnetic state as the state at time t equals 0 for a global quantum quench, where the state evolves with an Hamiltonian, that is the XX Hamiltonian, that on the other hand preserves the U1 symmetry. So this is the quench protocol that we're interested in. The tilted ferromagnetic state that evolves with the XX spin chain Hamiltonian. And if we want to apply the recipe that I showed you before, we should first compute the charge moments. And this is what we did. So the charge moments at each time t have this form. It was already known from this paper by Maurizio Fagotti, Mario Collura, Fabian Esler, and Pasquale, that asymptotically, in this particular kind of quench, the U1 symmetry has to be restored. So according to the comment I did before, Zn alpha has to go to Zn 0, and therefore this exponential should be equal to 1. This justifies this first line, so the equality between B and A for large values of t. Then we have realized by doing basically some numerical computations exploiting the free fermionic techniques, that at time t equals 0, the charge moments admit this nice factorization. So they can be written as the product of these trace, which are nothing more than the full counting statistics for this charge operator Q of A. Now, this full counting statistics was already known in the literature. In particular, here we also exploit the connection between the tilted ferromagnetic state and the ground state of the XY spin chain for a given in a given region of its parameters. But at the end of the story, basically, we were able to compute the stationary value for this function B, which is provided by the log of this product written here. Now, we have applied the quasi-particle picture. So if we know the asymptotic value that each excitations with a given momentum k contributes to B, and we know the number of quasi-particles that are shared between A and B at a given value of zeta, and which propagate with this velocity. So epsilon prime is the velocity of each quasi-particle. We were able to obtain a full expression for B for any value of time, or for any value of zeta. Okay, and here I show the comparison between our analytical expression, which are the black solid lines, and the exact numerical computations that correspond to this symbol for different value of n, l, alphas, and theta. Okay, so by doing the integral of these charge moments, one then recovers the entanglement asymmetry according to the recipe I showed you before. And here in this plot, I show again a comparison between our analytical predictions, so the solid lines, and the numerical results corresponding to these to the symbols. And from this plot, we can extract three nice features that the entanglement asymmetry has. So the first one is that for large value of t, we see that the U1 symmetry is restored since delta S vanishes asymptotically. And we were also able to extract how this quantity goes to zero. So this behavior as zeta to the minus third power, which is plotted in this in the inset. So it's these they are these dashed lines here. Another nice, interesting feature is that if we compare, for example, the dark and the light blue lines, which correspond to the same value of n theta, but to different L, we see that larger subsystems require more time to recover the symmetry. So it's important that the definition of the entanglement asymmetry that we have introduced is starts from Rovay and not from the full density matrix of the of our system. And another very nice feature that one can extract from this plot is that if we fix n and L now and we compare two different values of theta, so for example the dark blue and the green lines, the more the symmetry is initially broken, so the higher is the value of theta, the faster the symmetry is restored. And indeed, the blue lines takes less time to vanish with respect to the green line. And we dub this effect as a quantum Mpemba effect. Now, the Mpemba effect refers to the fact that hot water takes less time to be frozen with respect to the cold water. Now, since here this Mpemba effect, I mean, is contains the entanglement, is due basically derives from the entanglement, we call this as a quantum counterpart of the Mpemba effect. Okay, so let me summarize what I told you. I showed you a novel tool that is able to quantify how much asymmetry is broken, and we call this the entanglement asymmetry. And as an application, so to show the validity of this new object, I show what happens for a global quantum quench that starts from a state that at time t equals 0 breaks the U1 symmetry, so the tilted ferromagnetic state, and then which evolves with the U1 symmetric Hamiltonian. And we have shown the three nice features that the entanglement asymmetry has in this particular context, and one very interesting and counterintuitive feature is this quantum Mpemba effect. Now, starting from this, there are several possible feature directions that one could explore. For example, what happens if we start from a different initial state, so from the tilted nil state? Is the symmetry restored again? Or one could ask also, one could study this entanglement asymmetry also in the context of the XY spin chain, because when the parameter gamma is different from 0, we deviate from the XX spin chain that is U1 symmetric, and so one can study the entanglement asymmetry as a function of this parameter gamma. And another possible future direction is to apply the random measurement toolbox to this entanglement asymmetry, as it was recently done for other entanglement measures like purification, operator entanglement, symmetry resolution, and so on. And with this, it's all from my side.
Thank you, Sara. Are there questions? What? Gabriele.
Okay, little questions. The first one, is this this method based on the entanglement asymmetry the simplest method to check the restoration of the symmetry? This is the first question. I may think to check some kind of magnetization or whatever. And the other question is, what's the time scale of this restoration that you have found?
Okay, so yes, here the time scale does not depend on. I mean, there is not a nice relation between T and theta. I mean, with this tilted angle. We just observed that for larger theta, it takes less time, but I mean, there is no an exact relation between the values in which this goes to 0 and the values of theta. While about the possibility of using other tools, probably people did some studies that involved the study of correlation function in these kind of problems that break the U1 symmetry. But to the best of my knowledge, there are not other more efficient tools than these to explore how much asymmetry is broken in the system.
More questions? Gabriele, there is a question behind you.
Thank you. Thank you, Sara. And nice to talk to you again. It's Giuseppe
Ciao,
here.
Giuseppe. Yes.
Yeah, one question is connected to one that has just been asked, is why you choose entanglement to investigate dynamical restoration of symmetry, which is not one of the easiest quantities to compute in general. And the second one is if you have a simple physical picture, in this case, in the sense that here you have quasi-particle picture with which you can explain restoration of symmetry.
Okay, yes. So the fact that here we realize that larger subsystems require more time to recover the symmetry, I think that it's an important feature that one can extract starting from the entanglement in a given subsystem. So this is, I would say that this is one of the reasons for which using entanglement in this kind of context is, let's say, can be more fruitful with respect to other observables. And about the general picture, I mean, you are right. Since we have just introduced this quantity, this is the first and only example that we have studied in detail until now, and we could borrow some methods like the standard quasi-particle picture to study this. But yes, in general, I mean, we don't have yet a full picture of, for example, how to compute this quantity in a field theory setup, or I mean, in a more general scenario, let's say. So in this case, the quasi-particle was useful, but for other kind of quenches, like the one from the tilted nil state, we are still trying to understand what is the best way to study this object.
Also because there is not only one symmetry, no, even in this model, there are infinitely many. So you.
Well, yes, in this case, we focus on the U1 symmetry only.
Okay, so maybe it's interesting also interrelation between them, given that there are infinitely many. Okay, maybe we can talk.
Sorry, we have. I think we can thank Sara again. If you have questions, you can just go to Pasadena to ask questions.
Yes.